As we continue to get started on this topic, I want to emphasize one of the things that I read from this object design book in one of the previous videos a couple of lessons ago, and I copied it out here to my clipboard so I can read it to you. Our measure of success lies in how clearly we invent a software reality that satisfies our application's requirements and not how closely it resembles the real world. Now, one of the things that I may have said in previous courses when I was introducing some of the ideas like classes and properties and methods and kind of easing you into the thought process behind object-oriented programming, I said that object-oriented programming models the real world, and that's what makes it so powerful and so easy to learn, and it's how you simplify complex problems because you have a real world thing that you want to model, and then it's easy to model it, in the ethereal, conceptual world. So you can create a model of an animal, all right? And what does an animal have? All animals, let's just say, I know you're going to find some exceptions to this, but let's just say all animals have 4 legs, a mouth, 2 ears, 2 eyes, and so on. And then, hey, look, you can derive dog from animal, and you can derive cat from animal. You can inherit all those properties of animal, but you can specialize and override them with, for example, the dog will speak bow wow, and the cat will speak meow. All right, look how easy object-oriented programming is, right? Why don't you get this? Well, in reality, that's kind of a lie. It's kind of a misnomer. As that passage stated that I just reread, you don't model the real world necessarily. You create a model that satisfies your application's requirements. In other words, we take an abstraction of the real world and we call out those details that are pertinent to our application's needs. So the easiest example that popped to my mind was this example of a car. And we can model it a number of different ways, and depending on the way that we model it, it will lend itself to usage in certain applications and not in others. So what if we're modeling a car as it's being built on a production line and as we manufacture the car? Well, maybe we need to model the specific parts of the car, how many that we have on hand, the machines that are required to build them, and whether they're running right now or whether they're down, how that impacts our supply chain. Maybe we need to increase the number of parts based on the demand of a specific model of the car, whatever the case might be. Maybe we're not modeling a production line, the car in the context of a production line, but maybe in the context of a car lot. Maybe we need to just keep track of the make and the model and the year and the color, the condition, and the value of the car, or maybe who sold the car and who bought the car. Those aspects of a car are being abstracted out and modeled for the purpose of our car lot application. Or maybe we're modeling a car in the context of a service station or a repair facility. Maybe we're modeling an inventory of parts from many different manufacturers, many different models and years, and so on. Maybe we're modeling a car in the context of a traffic simulator. Maybe we don't really need the concept of the car at all per se. Perhaps we're really modeling specific roads and businesses and residential areas and speed limits and times of day. All right, or maybe we're modeling a car in the context of a self-driving car software. Maybe we're interested in how quickly the car can stop and accelerate, how quickly it can avoid an obstruction in the road, and so on. So you can see that even though there's a real-world car, there are many different facets and abstractions of it, and the way that we model the car in our application will depend on the needs of our application. So these all involve the concept of a car, right? But depending on our specific application that we're modeling, we're going to be interested in different facets of an automobile. We abstract those facets out into a model that describes the primary areas of focus inside of our problem domain. Now, the book, again, gives an example of a application that's built to replace a paper form that must be filled out. And the form is all about capturing information. You know, you hand a clipboard to somebody with the form and you expect them to fill it out with a pen. And the information is important, and we're definitely interested in gathering the data, but we're also interested in modeling how that data will be validated, how it's going to be persisted, what business rules will be activated, what activities will be activated by the data that's input. How are we going to manage simultaneous access by a large number of users? How are we going to limit who can actually fill out this form? All right. How do we identify who accessed the data after the fact, some sort of audit log, and so on. So in this case, it's kind of the opposite of the car example. Here, the abstraction is more complex than the physical manifestation of the form. The paper form is easy. It's just a simple piece of paper. There's not a lot to abstract away from it. But now we're talking about we're really not interested in a replacement for the paper form. We're inventing the object machinery, as the book would put it. And that object machinery fills a much richer set of concepts than what a paper form would at first glance require. So it's important to remember, object-oriented programming is not really about modeling the real world per se. It's although that may have been a convenient way to understand it from a high-level perspective as you were getting started. It helped you understand classes and properties and methods and functions and so on. But object-oriented programming is about abstracting the real world into a subset, perhaps a superset of objects that we need to consider for a specific problem domain and how to implement it as a software system. So in some cases, those objects will be our own creation, derived from our own imagination, that don't have physical or real-world equivalents. We create these abstractions because we're building conceptual machines that address ethereal conceptual needs like process, state, display, validation, persistence, and so on. Okay? So abstraction of the physical world into conceptual. That's what this video is all about. Hopefully you got that, and we'll pick it back up in the next video. Thanks.